So, Manuraptoran roots. These are the things leading to birds. This is part of that dinosaur renaissance we talked about briefly the other day. In the 60s, dinosaurs went from being, our interpretations went from being sluggish, stupid lizards dragging their tails to agile, active creatures. And this is an early reinterpretation of one of these small theropods called Deinonychus as an active and agile creature, kind of taking, a very lizard-like traditional dinosaur interpretation, but putting the tail out back and making him agile instead of that tail-dragging group that I grew up with. You guys didn't. There's the 60s interpretation. There's a more modern interpretation of this thing here. So we've got feathers. Feathers show up early in the theropods, maybe before. Feathers are essential for flight, which is where we're headed. So what's the deal here? What are these creatures doing with feathers? And we've touched upon this a couple of times. These animals were active, agile, a lot of muscle contractions and action, so they're generating heat. For a cold-blooded thing to generate more heat than it wants, has to radiate it off. But if you're generating that heat, your biochemistry works better at warmer temperatures. And so these agile, active creatures may have started to trend warm-blooded instead of just radiating the heat off as waste, using it and keeping their bodies warm. And if you're going to start burning energy to generate heat, you're going to want to save it and conserve it. And so feathers are thought to be initially an adaptation for heat conservation. And when we come to mammals, we're going to see the same thing with hair. But initially, this was about heat conservation. Almost certainly. They were fuzzy. These structures were there. They became more and more complex, and different functions evolved for them. They may have evolved for displays. Males talking to males, males talking to females, courtship displays. Maybe on the major part of the body, still insulation. We've got these arms here. We're grasping our prey with our fingers, our long fingers. One hypothesis is long feathers on the arms, which we in birds call flight feathers. That may have been, again, about display, or it may have been you're chasing a prey animal or a flying creature like a dragonfly, and that creates like a net, maybe to hold it down or to knock it out of the air. So that may have increased food getting success. May also be, like I said, about displays. So these are hypotheses about where feathers started as insulation, maybe later displays, maybe the ones on the arms about maybe forming a net. But we're moving towards birds here in this development. We're not flying yet at least. Okay. So here is what we've done. These are these theropod dinosaurs. And there are three major types that we can break down. Kind of functional types, not evolutionary groups, but kind of functional types. Three major types of theropods. And there are 1, 2, 3. I color-coded them there. One, the earliest ones, the primitive ones, we'll call these the slow movers. And I think everything's relative. They're faster than you are. These are the slow movers. And tyrannosaurs are a good example. Many of these were large. And these were big, fierce carnivores. They were chasing and running and grasping their prey, but they weren't real super agile yet. More agile things before them, but relatively speaking, slow movers. And I think tyrannosaurs are a good example. And again, tyrannosaur might have had feathers. I just found this cool picture of a tyrannosaur nest. So these little baby tyrannosaurs and their mom or dad. The next group move into a different niche, and we're calling these the fast-moving graspers. These guys and the ornithomimiosaurs are a good example here, that ostrich niche. These guys are a little bit more agile. They're chasing things down and grabbing them with their forelimbs. And again, probably feathered. Dinosuchus is a good example. All we have of him is his front legs, but he was a pretty big thing. and running around, grasping prey, maybe with feathers on his arms, helping in that form like a capture structure there. Here's a smallish example of this Sinosopteryx, Chinese lizard wing, is how that translates. And just an exceptionally beautiful fossil, that little animal there. About this big. Oviraptors are in this crowd as well. Even though they weren't eating eggs, they were carnivores. And a classic, well-known oviraptor is Caudipteryx, which means tail wing. I guess we have a fossil that shows this. Feathers on the tail. And notice how they're drawing these like turkeys.
It does look like a turkey.
Last group, these are called the hind claw slashers. The hind claw slashers on the hind leg, and they also call this is that Eumaniraptoria, but again, we're not worried about taxonomy. They have a big claw on that hind limb, and it's thought that these things slashed prey with it or defended themselves with it. And Velociraptor is in this crowd, which I assume means fast raptor. There it is right there. Isn't it interesting how the word raptor worked its way into taxonomy completely erroneously, and yet it's in all these words. All these little bipedal agile dinosaurs have raptor in their name. Now, in these guys, we see a couple really important modifications. Carpal is a wrist bone, right? Your carpals. And in these hind claw slashers, one of the carpal bones is semilunate. And what that means is, it's like a double, I don't know how to describe that shape, semilunate. Lunate is moon shaped, but it's got these two indentations in it. And they have this very distinctive carpal, semilunate, and it's in the wrist. They have really long fingers. It gives the wrist a motion, a twisting motion. And that's probably for grabbing and manipulating. But it's going to set us up for the motion that's needed to use that as a wing for flying. So remember we talked about pre-adaptations? This has nothing to do with flying, but it shows up for a food-getting adaptation. Also see the furcula, which is the wishbone again. Highly simplified and really well developed. And again, it connects across the front of the pectoral girdle. And again, probably about, this is a bird skeleton here, but probably about the mobility of those forelimbs, grasping and grabbing. But it sits right there, and if you've ever played with a wishbone, it's like a spring. And when we start moving these forelimbs like this, that bone, that furcula, that wishbone, is a spring that pops the wings back out as they come down. And that sets us up again for flying. It didn't adapt for flying, but it's a handy thing that the ancestors of birds are going to repurpose into flying. I didn't see Jurassic Park 3, but there's a cartoon about how it's stupid. And there's velociraptors without feathers. I think those are velociraptors. And there's an awesome picture of Ronald Reagan rescuing freedom from the clutches of ill-educated people, riding on a velociraptor, Spanish submachine gun for some reason, and a Russian RPG. Ronald Reagan was very suspicious of the Russians. Some people in the modern White House seem to have forgotten that.
And there's like the Indiana Jones fedora coming on.
Yeah. So anyway, we're off topic here. So anyway. Last group we're going to worry about here before we get to birds is Avialae. Birds are in this group, but this taxon here also includes pre-birds. So these are theropods that fly by flapping their wings. And we want to look at that. That would include birds and include some cool extinct stuff. Here's the first bird we know of. Called Archaeopteryx. It's a fossil you may have heard of. Pteros means wing. Archaeo means ancient or old or primitive. It's a beautiful fossil, and it's so well preserved in this very fine lithograph stone. It's on a lithograph quarry in Bavaria in the 1800s, that the feathers, the imprints of feathers, are preserved. If those feathers had not been preserved, paleontologists would have looked at this and said, oh, it's just another one of those little fine-boned, agile theropod dinosaurs. But the feathers, look how long the feathers on the arms are. We can start calling these wings now. And on the tails. This dinosaur could flap his wings and fly. Now, there were all sorts of things, probably jumping off trees and gliding, like a flying squirrel does today. But there weren't a lot of things doing this and getting lift. And that's an engineering challenge. Pterosaurs did it. We already involved flying. But bird flight with feathered wings requires a bunch of adaptations. And this guy brings them together for the first time. And there's a reconstruction of him. We're going to talk more about birds and flight when we get to the bird chapter, but we'll just do a little bit of it here. One of the most important things we see in Archaeopteryx that we don't see in earlier fossils is this kind of feather here. It's called an asymmetrical feather. Look at the two feathers here. This is a more primitive feather, and we've seen feathers like this. This is symmetrical. Either side of the shaft is equal. That's not a flight feather. You can't fly with that. But once you see these on the wings, we know this animal was flapping his wings and flying. And we'll talk about it when we talk about bird flight. But that kind of feather says, I can flap my wings and fly. This kind of feather might have been for gliding, or might have been for display or catching food, but that's not a flight feather. And there's an Archaeopteryx feather. It's a remarkable fossil. There's that peak end of the time, and there's the shaft. That's a flight feather. And that's one clear indication that we're flapping our wings and getting lift. Something like Caudipteryx, one of those earlier things, one of those fast-moving graspers or hindclaw slashers, had symmetrical feathers. And they may have been for displays. They may have been for gliding. They weren't for flying with flapping. So there's the difference. And then look at these bird feathers. There's a bird wing. You see the shaft? And very narrow, very wide. That's an asymmetrical feather. Okay? So keep that in mind. We're going to come back to that when we talk about bird flight. So there is another early flying bird. There's the fossil. Very unbird-like in many aspects of its biology, or its anatomy, I should say. Long tail. Birds don't have tails. Teeth in the jaws. Birds don't have teeth. There's lots of things about this that say dinosaur. But then the wings with feathers and asymmetrical feathers says bird. And that's a reconstruction. Were they good flyers? Probably not. But remember, when there's no one else doing it, and when you're the only one doing it, you're by definition the best. Okay. Here's hypotheses on where flight comes from. There's a couple. So we have these rapidly running or climbing or jumping active dinosaurs. They've got feathers. They probably have feathers on their arms for whatever reason, maybe for catching prey, maybe for signaling each other. But they've got feathers on their wings. Well, we'll call them arms now. We'll call them wings when they start flying. There's two hypotheses here. Or there's two routes to flight. And one's called the cursorial predator route. Cursorial means to run. And the hypothesis here is these animals ran fast and chased down maybe insects, maybe jumped and grabbed at flying insects. And when they jumped, or when they maybe jumped off the edge of a hill or off a log, with their arms out, they would catch some lift off those wings. off those arms. They had feathers trailing off their arms, put them out, and you glide. That's not flying, but that's the beginning. And so, light bone, fine construction, put my arms out, and I can glide. And so, that's called ground up hypothesis. We run and we catch some air and we glide. It's a cursorial predator. And in birds today, we have a beautiful example of a cursorial predator. I don't know if I haven't seen them around here. Do we have roadrunners around? Anyone seen one? It's a roadrunner, in case you didn't know. They can fly if they want to, but they don't very often. If you see a roadrunner, you disturb it, it'll run, it'll put its wings out and glide. But it spends most of its time running around. That's what we think the niche might have been in this scenario. Caudipteryx is a good example of that. He has symmetrical feathers on his arms, and may have been about display, may have been about catching some air and gliding. The other hypothesis, the other route for flight is similar, but it's not ground up, it's tree down. It's called the arboreal predator hypothesis. And this hypothesis, these little dinosaurs were tree dwellers. They climbed up into trees to feed. And again, they had those feathers dangling off their arms for display, perhaps, but they jumped from one branch to another and they put their wings out. I keep saying wings, their arms, they might catch some air. And so they start gliding. That's the tree down hypothesis. Something like this guy climbing up there and then jumping. And I mentioned a little while ago, what animal do we have today that does this? Flying squirrel. Yeah, they're not flying, they're gliding. And flight, either way, flight starts with gliding, either running and catching some air or jumping out of a tree and catching some air. And I'm not sure which hypothesis has more support behind it. You can model this. We can reconstruct these dinosaurs and make models, and flying is an engineering challenge. And we understand a lot about flying from an airplane perspective, and we can build models and test various constructions. And I'm not up on that, not a very functional guy, but some of these early birds, like Microraptor, had well-developed flight surfaces, we'll call them now, on their legs and on their arms. And kind of like a biplane with two sets of wings. We'll come back. There we go. We'll come back and talk about this more when we talk about birds. So, that's where we are here. We did theropods, and we'll come back and talk about birds after our next break. I didn't think I'd get to birds today, but I think we'll start birds after break. So, summing up the theropods. They took that ancient archosaur anatomy, think alligator, and they did this with it. Filled in all sorts of niches. And there's one group that's still with us today. So, remember our big picture dinosaurs. We did the bird hip dinosaurs last time, Ornithischia. These are the Saurischia, the lizard hip dinosaurs. We just did theropods. We got one more group of dinosaurs to play with, and those are called the sauropods. This includes the giant herbivores. These are where the giants are, but they're not all giants. Okay. As we talked about earlier, the basic anatomy of these guys was an archosaur, an alligator-like thing. The ancient sauropods, I used to call them sauropods instead of sauropodomorphs. The ancient sauropods moved into an herbivorous niche. And herbivory, you need different jaw construction and teeth construction. You need different digestive machinery. If they adapted for that, their anatomy changed. And one thing about this is finding a plant to eat doesn't require a lot of agility. So agility is important to get away from a predator, but it's not important for getting a meal. So agility becomes less of an issue for these guys. So in the sauropods are the giants. All sauropods are herbivores. And this is where the giants are, though not all of them are giants. And sauropod means lizard foot. And Marsh looked at those feet and thought they looked like lizard feet as opposed to a theropod foot, which looks more like a mammal foot. So some of the things we see here. We see, again, herbivory. These are niche issues, so they're shifting towards niches. What are they eating? Well, one suggestion is they were eating the vegetation on the tops of trees. And that promoted this really long neck. And the huge size falls in here, though, and again, not all of them are large, but the later ones are. Size is useful because you can avoid you can avoid being preyed upon. You don't avoid the predators; they just avoid you. Actually, that aspect of your niche a little more easy to deal with. We see, if we look at the various diversity of this guys, we see teeth specializations for processing different kinds of plant matter. That long neck for reaching up to the top of branches, that's useful. But then you have to hold that head way up there, and a big, massive head is not an issue. And one of the trends we see in the evolution of the sauropods is head reduction. It becomes smaller and smaller and smaller, lighter and lighter and lighter. And then particularly as we go large, we go quadrupedal again, down on all fours. So we see limb modifications for that. But also we see limb modifications for carrying around this really heavy weight. More about weight bearing than agility. Just to give you some scale, I looked and looked and looked for a picture like this. Can you see all the things on this picture there? This is a blue whale skeleton. That's an elephant. There's a person, and this is Brachiosaurus. These are the largest land animals we know about. So again, our starting point for all dinosaurs is a little agile bipedal carnivore. That's this guy down here. And there's hypothesized what he might have looked like. Early sauropods appear to have been smallish bipedal omnivores. And this is an hypothesized example of one of those. So the trend is going omnivorous and then herbivorous. And a good example of this animal is not a particularly large animal, but look at this name here, Panphagia. I eat everything. Phagia means eat, pan means everything. And his jaw is equipped with teeth that would work for plants and mashing up, or capturing animals and mashing up plant matter. Early on, these things are still bipedal, little moderately sized bipedal herbivores. We have some examples of them in the fossil record. As you get really big, you get bigger and bigger and bigger, bipedal isn't the route to go. Holding all that weight up on your hind two legs, having all that complicated machinery for digesting plants, and then these things tend to drop down onto their front legs more and more and more, and eventually we become quadrupedal. Plateosaurus is a good example of a transitional guy right in there. And the increasing size, as I said, promotes putting all your feet down on the ground. And eventually that's where we are. Did that. Rheogosaurus. So there's an evolutionary tree. You know, we've got some low-end ones down here, and then we move into the things that are more familiar to us, the big giants. So we've got low-end ones, kind of playing with their diet. They're trending more herbivorous. They're still bipedal, but they're moving towards a quadrupedal gait. And then we get fully herbivorous, fully quadrupedal, and that's the ones that are more familiar to us. So there you go. Some of them are so big that they were so big that early hypotheses were they had to stay in water all the time to support that weight. They couldn't walk around. It's not considered to be, that's not considered to be valid. That hypothesis is not considered valid today. They did walk around. There's someone's collection of plastic models. That's great. There are websites devoted to the collecting of these models, these toys. Some of them are ferociously rare, and on eBay go for hundreds of dollars. This one will set you back about $500. Unless a kid has played with it and scratched it all up. So, size. They're big. These are reconstructions of some of these things with a little person there for scale. And here's an example of some of those and the parts of the skeleton we have. And, again, we sometimes just get a femur or a humerus, in this case here, an enormous vertebrae. And when you just have a small part of the skeleton, we say, okay, we know it's a sauropod. We have complete skeletons of some of these other ones. We can scale these up. And the heads are very small, and the skulls are rarely found. They're fairly small, and they're rarely found in association with the rest of the body. So we don't have great information on all the heads. So examples of size if you filled out all those skeletons. This is one of the big ones, a recent discovery there. That was huge. An animal that big probably lived 200 or 300 years to get that size. Others were smaller. Celtosaurus was one. Elephant-sized, I suppose. That's relatively small. I just like that picture. With that size, we see a rearrangement, particularly of the feet. The limbs, they're not about fine structure, grabbing prey or running or agility. The limbs are about bearing weight and moving it around. And the toes are about spreading that weight out. What does that look like that lives today, that kind of foot? Big round foot. An elephant. There you go. Yeah, fairly similar. I don't want to say it that way, but the way it functions is similar. And these are trackways. We get trackways of these things. And when you're a big animal walking on a muddy riverbank, you're going to leave big holes. And various parts of the world, some of these have been preserved, and they're really kind of neat glimpse into the past. And there are experts in studying this. There are experts who can find, if you get several steps in a row all preserved, there's someone who can look at that and say, okay, here's how heavy it was. Here's how fast it was walking. Here's the sequence of how the legs moved. This is, anyone been to St. George, Utah? Go up there sometime. This is a dinosaur discovery. It's the city of St. George. And I've never been anywhere in my life. And I grew up in New Mexico and spent a lot of time in Colorado. And so I've seen cities that grow rapidly. And someplace in California too. I've never seen a city growing as fast as St. George. People were just pouring in there in the 90s and early 2000s. And this site here is a dinosaur footprint site, and there's a museum there now. That's the ground. And 20 years ago, it was way outside the city of St. George, and it was a farm. And the guy who owned it, his name there, Mr. Johnson. The guy who owned it said, "I'm going to cash in," and he was going to sell his land to developers. And in order to do that, he had to tear down his barn and his house, and so he got a bulldozer and he tore down his barn, tore down his house, and he noticed all these dinosaur footprints in the rock. And he called someone in to look at them, and he said, "This is really important." And this is what that guy did. He donated that piece of land to the city and said, "I'm going to donate you this piece of land if you build a museum over it." And so that's the kind of public-spirited thing we should remember. It's a neat place to visit. But it's off topic. So let's look at some more aspects of biology, these giants. They have this really long neck. And that's an engineering challenge. We've got a lot of weight to support. We've got to keep a trachea open for air passage. We've got to keep an esophagus open for food passage. We've got to process that stuff up here. So we have construction of a neck that's fairly different than other animals we've looked at. Weight savings in the bone becomes an issue. And these are neck vertebrae of one of these large creatures. We see the vertebrae linked together, which is not that unusual, so we get a nice rigid connection between them, flexible but strong. And then we see some weight-saving innovations in there. And one of those is, look at here, is what we call air sacs. Now, air sacs define birds, but they're showing up in dinosaurs as well. These are spaces in these vertebrae that are interpreted as air sacs. And that's just what it sounds like. It is a membrane connective tissue bladder into which air is introduced. And we'll talk about air sacs when we talk about birds, but they appear to have showed up early in these dinosaurs. Large spaces in their body filled with air that is brought in there through the mouth. These are called pneumatic bones. Pneumatic, as in pneumatic tool, and that would have lessened the density of the neck there with a weight-saving adaptation. And look at this. These are thoracic vertebrae. Look at that little Argentinian boy. Is it still over? I wonder where it is now. There's a huge vertebrae. Dr. Wheeler has it. Someone loaned it to him. No one's seen it? About this big. It's not a real one. It's a copy of one. The head, as I mentioned earlier, weight and a heavy head is not what we want. We want a head that's going to find the food, gather it, and send it on down the esophagus. And so the head tends to be small and simple. And like I mentioned earlier, we have a lot of skeletons for which we don't have heads. The head rolled away or broke up once the animal died. So, I mean, you might get a nice big skeleton and you dig and dig and dig and go, damn, the head's stuck there. The teeth are teeth for herbivory. They're for clipping and then mashing, in some cases, the plant matter. So not the big, sharp, recurved teeth like you'd see on a carnivore. The teeth for shredding and clipping vegetation, often from the tops of trees. That kind of tooth wears out. And as mammals, we don't replace our teeth, but a lot of reptiles can. And in the skull of this guy, it's kind of hard to see. There's rows and rows of teeth, and these are the ones that are being used. And as this tooth wears out, another one's pushed forward to take its place. And an animal might live 200 years. Teeth aren't going to last 200 years, so they're constantly replacing their teeth.
Like sharks?
Not necessarily sharp, but they're hard. And here's a piece of a jaw of one with the different banks of teeth visible inside there. We think that's weird because we're mammals and we can't do that. And there's a single isolated tooth from one of these with the wear surface, and that would just wear down until it'll be shed and another one would push into its place. You know about elephants, by the way, and their teeth? Elephants start their life, I think, with 6 pairs of teeth or 7. And they're these big plates, and there's only 4 in action each time. And when the ones in front wear out, another one pushes in, and that one's used till it wears out, and then another one pushes in. And they have 7. It's either 6 or 7 sets of teeth. And when the last one wears out, they starve to death because they can't eat anymore. So each set of teeth in an elephant lasts about 10 years. Off topic. Now, one of these big giant dinosaurs, and it was classically called Brontosaurus. And the correct name is, of course, Apatosaurus. But we made that transition, and it has to do with taxonomy and has to do with new discoveries. But it's a very simple story. It became very complex. Large skeleton was discovered, and the 2 dinosaurs are Brontosaurus and Apatosaurus. A large skeleton was discovered without a head, I think by Marsh. And so he slapped onto it a head that he had that was from an herbivorous dinosaur, and he put it on this big, huge dinosaur skeleton's body. And he said, here it is, and he called it Brontosaurus. And so there's that big dinosaur skeleton, and for, a century, it had this skull on it, which is just half of the skull he had lying around. And the Peabody Museum is there forever, and that dinosaur is called Apatosaurus. And later, more recently, someone figured out, there's the proper head. Not sure how they determined that's a much different type of dinosaur. And so the name Brontosaurus was discarded, and the proper name is Apatosaurus once we put the right skull on it. But here's some toys. And the Brontosaurus head is a big, heavy, blunt thing. And the Apatosaurus head is a long, thin thing. The older version of Brontosaurus has a big bull head. There it is there. And the current version, the modern version, if you will, That's a little bit of taxonomy, priority of names, and confusion. So old version, new version. So niches of these guys. We've kind of been talking about this along the way. They're herbivores, and plant matter is a challenge to digest. And remember, one of the traits of archosaurs is a gizzard, a muscular gizzard, which is a chamber leading to the stomach. And many of them had gizzard stones, and they would swallow these rocks, and they would roll around in there with the muscle contractions and grind the food up. They didn't have a lot of grinding structure up here. Most had clipping and swallowing structure. Grinding happened down here. And imagine that a stone's in a dinosaur stomach for 150 years.
Yeah.
It becomes almost round, almost spherical, and highly polished. Okay. There's some other examples here. Diplodocus is one. And these giant ones that had a really long, thin tail. Brachiosaurus had really long front legs. It kind of stood up a little higher. Brachiosaurus also had its nostrils on the top of its head, which is why some people thought maybe it sat in water and just stuck the top of its head out to breathe, but that's not thought to be the case now. Mamenchisaurus has this enormously long neck. It's from China, I don't know, from China. So, neat variation there. Did that. Where am I here? Give an example of size of the big quadrupedal ones. There are some small ones, but in general we're talking about fairly large animals. There's a tyrannosaur for scale there. So you can imagine when one of these died, or was injured or killed, that was quite a meal for a while for a bunch of creatures. Look at this one here, Nigerosaurus from Africa. Nigerosaurus, no A in there. And look at the teeth there. Very broad bill there, fine little clipping teeth. There's a reconstruction. What he was eating? Don't know. I'm sure someone has a hypothesis, but that's very different the arrangement we see from anybody else. There's a reconstruction. This one's interesting. Lets us look at modern biology and measure with dinosaurs. Europasaurus. Typical little sauropod. There's the skull. We got those teeth for cropping and stripping vegetation. What's unusual about Europasaurus is its size. A very small sauropod. An adult there and a juvenile there. They're, horse-sized. In a group where most of the species are really, really large. Hypothesis here is it evolved on an island. And one of the trends in things that evolve on islands is they get small. The food resources on islands are limited. So having a really big body you have to feed becomes a challenge. And island things, in many cases, get smaller and smaller and smaller. And these are the Channel Islands here. Right here, Anacapa and Santa Cruz there. And we have examples on our islands of dwarfing. Out on the northern Channel Islands, we used to have a pygmy mammoth, like a woolly mammoth, elephant-sized normally, but the species that lived on the islands was the size of a horse, the pygmy mammoth. That's really cool. You can go to the Park Service headquarters and see a skeleton. And then there's this for a living creature. You've been out to Santa Rosa or Santa Cruz and seen the foxes? Go out, they're adorable. It's a fox, but the adults are the size of puppies, big puppies. And you look at the skulls there, mainland fox, Channel Islands fox, about maybe 2/3 the size of the mainland thing, maybe about half the size. So mainland, its closest relative, out on the island. So when we go out the islands, we almost always see them anymore. They've made a comeback. They were critically endangered about 10, 15 years ago. They made a comeback. And one of the fun things about going to the island is tracking them down. And you don't have to track very hard because they evolved on islands, and island creatures often have no fear of humans, which is not healthy. But they didn't evolve with predators. They often don't have any fear. And these little Channel Island foxes, sometimes they'll run through your legs in the campgrounds, or they'll sit right there. And then again, you shouldn't approach them, but you can get fairly close and just snap pictures away while they stare at you. We went to Santa Cruz with my daughter a couple summers ago, and she really wanted to see one, and the only one we saw was standing on a picnic table licking grease off of someone's camp stove.
Ew.
Okay. So dinosaurs, let's close them up. Here they are. Well, let's just do this one here. Dinosaurs are classic archaeosaurs. You got all the trace. The primitive one, or the first branch that came off of the bird-hipped ones, ornithish, yeah. Then we got a radiation of saurischians. Theropods lead the birds. And another group went herbivorous and became sauropods, yeah.
So why do you have birds coming off before theropods if birds are
well,
theropods?
I just wanted to put them there. We should probably...
Okay,
we should
that was a
probably-
little confusing.
Let's do that, yeah. Let's do it like that. That's inconsistent the other way I've been drawing it. So archosaurs start off with crocodilians. We also have pterosaurs. And then we have the dinosaurs, ornithischians and saurischians. We got a couple more things we have to handle, and then we'll call it a day with this ancient stuff and we'll start birds. We've got to handle the aquatic stuff. There are no aquatic dinosaurs. There's dinosaurs that walk into the water, maybe dinosaurs that swim, but the truly aquatic Mesozoic reptiles are not dinosaurs. We'll come back and we'll get that word later. Sauropterygians and mosasaurs and ichthyosaurs. These are all, none of these are dinosaurs. And then when we get to mammals, which is maybe Friday, probably Monday, there's other cool Mesozoic stuff that are not dinosaurs, but probably were in your bag of plastic dinosaurs when you were a kid. Now, one more ancient thing I want to do, and that's the aquatic thing. So we'll start there, and then we'll take our second break, and then we'll push on. Get rid of that. All right. That's just a little sidelight here as we move to aquatic things, and kind of what we've been doing all along. I've been saying sometimes you only have a vertebrae, or you only have part of a jaw. Sometimes you have highly fragmentary fossils, and you want to interpret them as best you can. So here's a dinosaur, Brontomeris, and these are the pieces of it that were recovered. Enough to know that it was a sauropod, particularly we have the hips. Big ribs there, but not enough to know a lot else about it. But we can reconstruct what the rest of the dinosaur might have looked like because we have close relatives. Camarasaurus, we have several really good full skeletons of that. So we know, okay, this is that version of dinosaur. We can use this as the model to fill in the species on that one. So there's some old, I don't know if it's Plato or something like that. There's a little, oh, I think I got the wrong, I loaded the wrong version of this. Yeah, as usual. This is the edited version. There's an old thing with Plato. So you have a blind man describe an elephant. And there's what he says, an elephant's like a rope, an elephant's like a brush. You know, if you only have one or two pieces of it, you might get some really bad ideas or incorrect ideas. So I like that part. An elephant is soft and mushy. That's often where we are with dinosaurs, I think. So let's look at the aquatic ones. So the Mesozoic aquatic reptiles, they were in your bag of plastic dinosaurs, but they are not dinosaurs. They're not part of Dinosauria. But nonetheless, they're pretty cool. Look at that food chain there. A Mesozoic food chain. So here's our evolutionary tree. And here's what we've done. There's the archosaurs, okay? Crocodiles, pterosaurs, dinosaurs, birds. There we go. There's nothing aquatic. Well, there's aquatic things, like I showed you that Spinosaurus would probably swim. But the truly adapted aquatic things are elsewhere. The things we call plesiosaurs, think Loch Ness Monster. Ichthyosaurs is like a dinosaur version of a dolphin. Mosasaur is like an alligator. That's not a good example. Big swimming lizard. So these are things we want to talk about real quickly. These ancient things, the ancient aquatic things. So there we go. Three types of animals here. Now, remember the lepidosaurs? Snakes and lizards and tuataras? Mm-hmm. Okay. These guys are lepidosaurs. The sauropterygians, that means lizard fin. Sauropterygian. That's like the Loch Ness Monster. It's really more of a lizard-like thing. Well, it's a lepidosaur than it is a dinosaur. And mosasaurs are actually lizards. So, sauropterygians right here. There's the lizards here. They're in that group there. And they didn't put mosasaurs here. Mosasaurs really are lizards. Or they're like monitors, like the Komodo dragon. And these guys are over here in lepidosaurs. The ichthyosaurs, which are like dolphins, they're really unclear where they go. They're so highly modified in that super specialized swimming niche that the clues to their relatives have been washed away in evolution. So they're unclear what they are. A few things. Aquatic living increases the chance of fossilization. When you sink into the mud on the bottom of an ocean or a river or a pond, there's a greater chance to be fossilized than if you die on an arid plain and the hyenas rip your body apart. We've got good fossils for a lot of these things. Let's look at the sauropterygians. Again, that means lizard fin. Oh, no, we're not looking at them yet. And the two we have sauropterygians, lizard fins, and then ichthyosaurs. Again, think a dolphin, but a reptile version of a dolphin. Ichthyosaur, that means fish lizard. So both these groups have adapted to aquatic living. And something interesting has happened. I'll hit it real quick. It's fun to do anatomy every once in a while. They're diapsid animals. They have their ancestor had a diapsid skull, and I don't think we have to talk about that too much. Again, the two openings in the side of the head, temporal region. There's our thing, our different types of skulls, anapsid, one opening, mammals and ancestors, two openings. That's where we've been for quite a while now, the diapsids. Well, damn it, there's a third kind, and it's called euryapsid, and it appears to be a modified diapsid skull. And it's got one opening in a different place than this one opening. So it's called a euryapsid skull. And that's what these guys have. The ichthyosaurs and the plesiosaurs have a euryapsid skull with that one opening in a different place. And if we look here, there it is. So that's different than we've seen before. It's a different kind of skull. Look at this. When I say Loch Ness Monster, you can picture what I'm talking about, right? And there's an ichthyosaur with that single opening right there. That's the one that looks like a dolphin. So they show this common feature in their skull, and it's sometimes taken as an indication that they are related to one another. And more currently, people are looking at it and say, nah, it's just two different lineages did the same thing. It's not an indication of relationships. It's just accident of evolution. They both look the same, but it's a different way of being it. Now let's look at the plesiosaurs. Plesiosaurs and pliosaurs, their fancy name is sauropterygian. I'll say it one more time, it means lizard. Lizard fin. There's a skull, nice euryapsid skull. When we look at when we look at these things, we see something that extensively modified for aquatic living. Highly adapted. The anatomy has been jerked around for aquatic living. When something is so specialized like that, sometimes it makes it a little bit difficult to determine the relationships, because the pieces of bone you want to look at have been modified to such a degree they're modified for swimming now, and they don't show the ancestral traits. And as an example of that, this is not a dinosaur, but this is a creature called a tongue worm, about this big. It's a parasite. It lives in the nostrils and sinus cavities of turtles and lizards, big lizards. So it's a snot parasite. And you look at that, it's so incredibly adapted to that niche, living in nostrils, that you don't see what it is. It's hard to look at that and say, what is that? That's an invertebrate. I'm guessing you're looking at it and trying to figure out what group of invertebrates that belongs to. It's a crustacean. Most closely related to crabs than anything else. But you don't see it when you're looking at the anatomy, unless you look very closely at the larva. So that's kind of what I mean with these aquatic dinosaurs. They've been jerked around so much, their ancestry is a little bit of a challenge. So what are we talking about with the Sauropterygians? Well, there they are in our evolutionary tree. They're lepidosaurs. They're close to lizards and snakes, that crowd there. That's the general consensus. Put a question mark there, because we can put a question mark by almost anything. So these are their closest living relatives. The origins, and kind of like flying, we got transitional phase. You got running creature, gliding creature, flying creature. With aquatic things, you've got a terrestrial tetrapod adapting to aquatic life. You're going back into the water. So we see some kind of transitional phases there. What's a mammal that's kind of terrestrial and yet adapted for aquatic life? But that's a mammal. I'm talking mammal. That's a bird.
Polar bear?
Polar bear is a good example. How about something that's a little bit more aquatic than a polar bear?
Seals.
A seal or a sea lion, yeah. That may be where these kind of things started. Not a seal or a sea lion, obviously, but something like that. So you got some transitional there creatures here. You got the full-on aquatic ones, and then the ones that are kind of going that route. And at the bottom end, the placodonts, maybe like an otter, comfortable on land, does okay in water as well. And these guys were pretty common early on here. And they have these big, heavy teeth. Placodont means plate teeth. They have these big, crushing teeth in their skulls. And look at that. Like a grinding mill. And it's assumed these things ate shellfish. And these ancient ocean bottoms were quite rich in things like brachiopods and certain kinds of mussels. So these guys are probably rooting on the ground eating shellfish and adapting to aquatic life, probably in and out of the water like an otter is today. It's a reconstruction. Here's a funny one. What's that remind you of?
Turtle.
A turtle, yeah. Not a turtle, not closely related to turtles at all, but similar construction, maybe evolutionarily responding to the same things early turtles responded to, probably making himself too big for a predator to eat. So these are early. They disappear by the end of the Triassic. They give way to another group that a couple of other groups that are a little bit more aquatic. Maybe in and out of water still, but a little bit more comfortable in the water. Pachyopleurosaurs. Get a name we don't need, but we have to give everything a name. And nothosaurs. So in and out of water, that's not a shellfish crushing set of jaws. What do you think these guys are eating? Fish. Yeah. Sharp teeth, not necessarily really heavy jaws. That should suggest they're eating fish. Here's a reconstruction. So kind of a transitional thing to something that walks into the water to eat shellfish, something that's in and out a little bit more. And like I said, there's that sea lion niche is what I'm imagining for these guys there. Up on land, they're reasonably comfortable on land, but they probably don't stray very far from the water. Full-on aquatic ones start with pisteosaurs, and we start to see fingers disappear and toes disappear, and these become flippers. If this thing came out of water, it probably did so only in emergency. But they don't show features that we're going to see later of the exquisite swimmers. So there's someone's idea of what this ancient Triassic ocean might be. The full-on aquatic ones are plesiosaurs and pliosaurs. And again, I keep saying Loch Ness Monster. That's what we're talking about here. And these are the guys that show full-on aquatic adaptation. So this is not seal or sea lion. It's really not probably quite whale yet either, but that's what we're moving towards that. These are swimming specialists moving around these ancient oceans, chasing down fish, chasing around ancient invertebrates, squids and things like that. They show some unique features. Here's a pectoral girdle of a particularly nice big skeleton, and they have a unique shoulder girdle that allows them to do this. Nobody else can do that. Well, you can do it, but not quite like they can. A unique construction there. And this is another skeleton. Early artists drew one coming out of the water. They probably didn't, any more than a whale comes out of the water. Diet, well, we have some clues on that. Certainly the teeth suggest sharp teeth. That's not a particularly robust bill or jaw. That's not tearing things apart, grabbing things and swallowing them. And so in those Mesozoic oceans, we think they're swimming around chasing fish, and were very abundant at the time, but also these shelled mussels like chambered nautilus. We call these things ammonites. You may have seen fossils of them. It's like, can you picture chambered nautilus? That pretty curly shell with a squid coming out of it? Yeah, this is an ancient version of that. And that, they're particularly abundant. This is thought to have been their food. And of course, fishes were quite abundant at the time. There's a skeleton of one, preserved well enough, and it was collected with enough care that gastroliths were found. Those grinding stones aid digestion. They're eaten. I normally associate gastroliths with an herbivorous diet, but these guys are using it to grind up maybe the ammonites they're swallowing. Since they're not coming up on land, it's almost certain that they gave live birth. They're not laying eggs in water. They're not laying amniotic eggs in water. So almost certainly live birth. And here's a fossil that appears to show an animal with a juvenile and embryonic skeleton on the inside. There's confirmation of that hypothesis. And there's a drawing there of mom and a baby. Parental care is considered likely. Plesiosaurs are the ones with long necks. Pliosaurs have big muscular necks. I think in one of those Jurassic Park movies, I didn't see any of them. I remember seeing clips of when he's jumping out of the water at like a show. That's probably what that was. So plesiosaurs, long-necked ones. And they ranged in size from people size to really, really big. Pliosaurs, like I said, don't have big, long necks. More robust, more alligator-like in a lot of ways. And those got big, too. So, there's a pliosaur skull with a T-Rex skull for scale. I just think that's a cool drawing. Liopleurodon. This is just a really weird one, and it's a nice skeleton, and in particular the skull is rather odd, and that's a reconstruction of it. It's got a rather weird arrangement of very small teeth and a cleft in the upper jaw. That's rather odd. That's a reconstruction, and that may have been what they're portraying here, sifting through the detritus for small invertebrates, and this would have been the filtering structure there. So I don't think we have a niche quite like that today in anything. All right, let's take another quick break. There's again ENC. So put your pencils down for a few minutes, or your pens, and we'll finish this up and maybe get to birds. All right. I'll be right back.